as rho natural, you take as sigma natural, and this is as beta, and this is as S by rho by kernel beta, and this is as kernel beta natural, and this is as alpha. So basically you see, we know that from S to S by sigma, this map is what? Homomorphism map, correct? This map is a morphism map, and now you assume this as a T. Assume this is a T and apply theorem 1.5.3. You first apply theorem 1.5.3. You assume this as a T. See, S from S to T, what you have? You assume this as a phi. Phi is a morphism from S to T. Then what you have? S to S by rho. You have rho natural. Then by theorem 1.5.3, what you have? Remember, there exists unique morphism from S by rho to T, that is S by rho to sigma. You have this thing. But to apply this theorem, one thing is that rho must contain in kernel phi. So rho must contain in kernel of, first you can apply this theorem. You can apply theorem 1.5.3 only. Why? Because rho is contained in kernel sigma natural. That's why we are applying this theorem 1.535. We have beta is unique morphism, such that what we have? Such that image beta is equal to what? Image beta is equal to image phi. This we have. Now first assure that rho is contained in kernel of sigma natural or not. Correct? See, what is kernel sigma natural? Kernel of sigma natural, if you calculate, A comma B belongs to what it is. Yeah, you can think also like this. You take A comma B belongs to rho. It implies what? A comma B as rho contained in sigma. It implies that A comma B belongs to sigma. It implies that A sigma is equal to B sigma. Correct? It implies that A sigma natural is equal to B sigma natural. It implies that A comma B belongs to kernel sigma natural. So in this way we have shown that rho is contained in kernel sigma natural. So by theorem 1.53 we can say that there exists a unique morphism beta from S by rho to T. T is what here? S by sigma. Correct? So S by sigma. And also image beta is equal to what? Image phi. So image beta is equal to image phi. And what is image phi? Image phi, what is phi? Phi is what? Basically image of sigma natural. And image of sigma natural is what? S by sigma. S by sigma, it implies that beta is what? Beta is what? Onto, we can say. Because image beta is what? S by sigma. Because image sigma natural is what? Sigma natural is onto map. So it is S by sigma. So image beta is equal to S by sigma. It means what? Beta is what? Beta is a map from S by rho to S by sigma. Correct? And image of beta is equal to S by sigma. It means that beta is onto map. Correct? Anyway, so we get this thing. Now see what we have to prove. We have to prove that. Now you see, now by theorem 1.5.1 This is by 1.5.3. Now this is you say now by theorem 1.5.2. Now assume this as this is S and you say this is T, correct? For example, if this is S, for example, assume just I write just dot. I am just writing a dot so that all of you don't confuse for that. If you assume this is S and assume this it is T, so you have this as a morphism, correct? This is a morphism, correct? Now what is theorem 1.5.2 is what? If phi is a morphism from S to T and S kernel phi naturally is from S to S by kernel phi, and kernel phi is what? Of course it is a congruence. So you see kernel beta, if you talk about kernel beta, since beta is a morphism, so of course kernel beta is what? Congruence. Beta is what? Beta is morphism. It implies that kernel beta is what? Congruence. Congruence on what? Congruence on S by rho. Correct? So kernel beta is a congruence on S by rho. Now kernel beta natural, just you see theorem 1.5.2, kernel phi natural is a map from S to S by kernel phi. So kernel beta natural is a map from S by rho to S by rho by kernel beta, correct? So now you have a morphism, monomorphism. This alpha will be what? Monomorphism such that image alpha is equal to image beta, correct? Image alpha is equal to beta. What is image beta? Image beta is what? S by sigma. It implies that alpha is what? Onto also. So alpha is onto. Alpha is mono, alpha is morphism, alpha is also onto. It implies what? So S by rho by kernel beta is isomorphic to S by sigma. This is by theorem 1.5.2 we have. So we apply both theorems, theorem 1.5. First we apply theorem 1.5.3 and then we apply theorem 1.5.2. So by applying these two theorems, we conclude that these two semigroups are isomorphic to each other. Why? Because by theorem 1.5.2, this is what? Monomorphism, that is 1 plus homomorphism. And also you see image alpha is equal to image beta, and image beta is already, we have proved S by sigma. So S by sigma, so alpha is what? Onto. So now it is isomorphism. So what is rest? Only thing is that we have to show that kernel beta is equivalent to this, rho by sigma. If we are able to prove this, then we are done, correct? So now let's prove. So now we show that kernel beta is equal to rho by sigma, correct? Now you see to prove this, of course, what kind of elements kernel beta will contain? It contains, take any A rho comma B rho belongs to kernel beta. It implies, it is in kernel beta. It implies that you say that kernel phi, it means that A rho beta is equal to B rho beta. Implies we can say that, correct? So A rho beta is equal to B rho beta, and of course A rho beta into B rho beta, it means what? Beta is a map from S by rho to S by sigma. So how A rho beta is defined? Of course, it implies it will be A sigma is equal to B sigma. Now, A sigma, B sigma. A sigma is equal to B sigma. It implies that A comma B belongs to sigma. It implies that A rho comma B rho belongs to sigma by rho. So A rho comma B rho belongs to sigma by rho. And it means what? Both sides become equal. So kernel beta is equal to rho by sigma. So rho sigma by rho. So sigma by rho is what? Congruence. Because kernel beta is a congruence, of course. Beta is a morphism. Kernel beta is a congruence. So rho by sigma is what? Congruence. And hence now you can replace S by rho by sigma by rho is isomorphic to S by sigma. So in this way, this theorem is proved. So read again and again this theorem. For any problems, all of you are welcome to discuss with me. So today we stop here.